yeah, we kind of have some hard swingers here. John is the Network Operations Manager at the ITS Division at UCSC. He is the current chair of the HPR TAC, and he's involved with the Science DMZ implementation at UCSC. Roger is the network architect at UC Davis. He participates in and has chaired the HPR TAC. Roger contributed to writing UC Davis's CC-NIE proposal and is participating in its execution. Eric is a principal network engineer at UC Berkeley. He's a principal person implementing Berkeley's Science DMZ. Eric is a past chair of the HPR TAC. And finally, we have Brad Smith, and he is the Director of Research and Faculty Partnerships at UCSC's ITS Division and an adjunct faculty in computer engineering. Brad's activities at UCSC include resolving researchers' IT bottlenecks and research and teaching on computer networks. So I guess we're starting off with John.
We're starting off with Eric.
Eric, okay.
What we'll do here is Eric and Roger and I will run through what the topology looked like at each of our 3 campuses, and then we'll just sort of have a discussion about what problems we have tried to solve, how we've gone about it.
So when I volunteered for this, I had hoped that there would be more progress done on our campus in our Science DMZ implementation before this panel. But in fact, we've gotten to the point of purchasing hardware, but we haven't done any implementation. We have the plan for what we're going to do. Let's see. And this shows kind of an outline of our Science DMZ as we envision it being installed. Over on the left-hand side of the picture, you can see kind of just a bare skeleton of the campus network. And our Science DMZ, which comes out of a successful CC-NIE proposal that we were awarded last year, will add the 100 gig link from the CalRen networks into one of our border routers, and from there a 100 gig link over into an EX9208, a Juniper switch, which will be the core of our Science DMZ. From there, the Electrical Engineering and Computer Science Department is also installing a bunch of open flow capable 100 gig devices where their researchers will connect. Other researchers on campus will connect directly into the core Science DMZ. So it's going to be a Science DMZ that's kind of spread between multiple administrative domains on campus with the EECs, but then also spread over into our data center. We're ramping up some HPC stuff over there. We haven't gotten to the point of figuring out exactly what we're going to do, but we do plan on stretching Science DMZ capabilities. Another thing you'll notice is on every device here we have a perf sonar node, probably a couple of them, in order to provide instrumentation so we can test, find problems, hopefully find problems before they actually crop up and cause issues for users. Another part of this doesn't show it, but another part that the CC-NIE has helped is encouraging us and getting us started with reaching out to the researchers, finding the people who have networking problems so that we can hopefully help them fix it. I think that's pretty much just a brief description of what we're doing, and then later during the discussion we can get into more of the details.
Are all of those in a common AS?
So the question is if all of these are in a common AS. I don't know if we've made that decision yet. That's something I haven't really thought about. It's a good question. Currently, EECS does connect to us with a different AS into the campus, but this will be the research side, and so I don't know exactly how we're going to do it. So I think Roger or John is next.
Oh, okay. So Eric has presented a plan, and what we have at Santa Cruz is sort of a progression from what we had in 2012, where we had several research projects down here that were behind 1 gig or 100 meg links to what we implemented quickly last year in order to solve some of their connectivity problems by placing a little Science DMZ router, which is actually a Cisco 3560E with 10 gig dedicated uplinks into the border that serves several science projects. This was sort of our first step into the concept of a Science DMZ, where we placed some equipment that we thought would be cheap and easy to upgrade. We didn't have to do a forklift upgrade to the core in order to think about fixing bandwidth problems for those folks with those projects. And when we, so this is the CC-NIE funded topology that we're about to implement, where you can see the fat green 100 gig link into CENIC, the new NIE router that will have a 100 gig interface and will fan out multiple 10s with giving us a ability to lag 10s for high bandwidth projects. What I didn't draw on here was the perf sonar nodes that are also part of the project, and there will be perf sonar node on the NIE router, and there are also fast data transfer nodes in here that will help to bring some of the traffic local. And where we are with this particular picture is that the stuff is either in procurement or in planning. We have not yet made a decision about what the NIE switches will be. So Roger actually has one of these working.
Yeah. Because I kind of, oops, wrong way. Ours is a little bit different. We started off with having a Science DMZ that wasn't called a Science DMZ yet, about 5 years ago, and it was a collapsed backbone switch that sat on a 10 gig link behind our border router and used and shared the HPR uplink into 10 gig into CENIC. We decided to do it different this time, partly to be different, and so we're running our 100 gig straight into the CENIC network rather than passing it through a border router. This is truly no seat belts. One of the reasons we did that is one of the researchers, actually the co-PI, is interested in what attack vectors will actually come at us. And since we're kind of sitting there just waiting for attack vectors to happen, our operations people weren't too comfortable with having that go through the campus border. So that's how that happened. Oh, in the 5 years of running the previous incarnation of it, we didn't have any attacks. So it may be that our co-PI is disappointed. Let's see. We do BGP with CENIC on that link, and we also do BGP with the campus border router, and the Science DMZ is in our public AS, is behind our public AS, but it's a private AS. Another thing that we're doing that's a little bit innovative, I think, is that we're running classic IP on some of the ports, and we're running OpenFlow on some of the other ports. And that's to satisfy two different categories of researchers that we're serving with this. We have researchers that are there with big data that just want a fast pipe, and they're using the classic IP approach. And we have network researchers, a group called the Next Generation Networking Laboratory on campus. It's about 8 researchers that are intensely interested in new protocols, and we're putting them on the SDN side. That 100 gig uplink carries one VLAN for the layer 3 traffic for the big data users. It has a few VLANs for layer 2 connections, and it also has a a SCAD of VLANs as OpenFlow resources, including Genie. We're running Floodlight and Open Daylight and Flow Visor on the controller that you see in the picture. And the researchers have control of that. They each have a different focus in the kind of research they're doing in this situation, but they seem to be sharing really, really well, which is good. When we were, once we had our original research network in, we realized that the researchers had a barrier to using it, and that was they didn't have the money for fiber to their labs. So we pulled out of our own pocket enough money to get fiber to the next generation networking lab, and we went ahead and built an SDN test bed for the researchers to use. It consists of 5 HP switches and 2 Arista switches. It's shaped like that, with the Science DMZ on the left-hand side, the 2 Aristas being the top of this architecture, and the 5 HPs being in each of the 5 labs. The researchers are still even facing difficulties getting things like patch cords and network interface cards, and I think we're going to be helping them with that too. I think what's really going on here is they have to have things in place in order to propose their own research and get the grants. So it's kind of priming the pump. That's pretty much it.
Is there a second row of things that are just barely visible there? Or is that some visual artifact?
That's possibly Rev 2.
Sure, dive in.
So, in anticipation of the infrastructure that John described, we started talking with the faculty, with the researchers who we had originally targeted in the proposal to begin to get a sense of what kind of stuff we needed to deal with to help them make use of this new infrastructure. And this is focusing mostly on the big bandwidth guys. The SDN component of the project is sort of held off till later years. The 3 big main groups that we were talking to when we created the proposal were the Santa Cruz Institute for Particle Physics, which through the ATLAS program does a bunch of LHC downloads. The Heidi's cluster is actually, the PIs on it are all astrophysics researchers, and it's this largish cluster, like 6-rack cluster, that we're in the second generation of working with astrophysics guys and having a local campus cluster that they can use. They've gotten quite addicted at being able to allocate their own resources for graduate students and things like that, as well as a number of the faculty's projects. What they're starting to use this a lot for is they do these huge computations on the big national labs and then download data and, well, prepare their code locally, run it on the big things, and then actually do some post-processing locally. And that's branched out to a whole bunch of different departments. We got astronomy, I show you there. Applied math and statistics has gotten involved over the past few years, earth and planetary sciences. So that's a whole group of folks using this one sort of largest, like I said, 6-rack cluster. And then the center, CBSE, Center for Biomolecular Science and Engineering. And you'll, well, no, the picture was in the one John showed. They have the Cancer Genome Browser is one basically global resource they provide to allow a nice interface for folks to do comparative genome browsing, basically. And the Cancer Genome Hub, which I'll talk about here, although I don't have a picture for it. So looking at the SCIP situation, what we've, in talking with them, this has been over the past month, about what their challenges are. We uncover some interesting situations. The SCIP guys, this is the picture of what their infrastructure looks like. And what it turns out, the big issue, they actually, we had upgraded, as John had mentioned with this IDMZG, a lot of this connectivity to 10 gig. And they just recently were able to get their environment upgraded to try and take advantage of that 10 gig. Before this, they had 1 gig connectivity to the outside world at this. Are you seeing this?
Yep.
Yep, good. On this link here, this was limited to 1 gig, but they upgraded it, I'm going to say in the last month, to 10 gig. And this, in particular, the flow is, there's a lot of activity going on here, but the one that came out in the conversations with them is they basically have data coming in from the campus network going to this node here, this Atlas 4 node, which then fans it out to these xrootd clients, which is some sort of user space kind of distributed file system to save the data, and then they run a bunch of stuff on it and get their results. When they upgraded the links from campus network into the switch and then from the switch over to the Atlas, or both links to this transfer node basically, they didn't get anywhere past 1 gig. It didn't really improve their bandwidth, interestingly enough. So we did some talking with them ourselves. We got ESNet guys in on a call to work with them. And it turns out what the general thought from the ESNet guys is that they need to they want a clean path from the campus. They don't want this we're basically having to separate the flow from the campus network to the node away from the switch that is doing all this traffic from the Atlas file transfer node basically to the file servers. And the problem there was these are all 10 gig links going to these 1 gig links going to these file servers, so it was, the feeling is, the guess is that it was chewing up all the buffer space in the switch. And the general philosophy we got from the NSF from the ESNet guys is you want to have the path into your environment be nice and clean, nothing competing for it, and then you can do whatever you want on the other side of that. So what we're going to be doing is moving this link from the Atlas, from this file transfer node basically to the campus network to another switch in the little subnet that all these things are connected to. But it was interesting because we dove into this and there was a whole lot more moving parts than I mean, some of us, Jim was probably aware of most of it, but it was an educational experience. The next one is the Hyades, the cluster. We have one guy, the guy who's actually an astrophysics PhD, who came out of this group is also the person that administers the whole system. He's working with us as a part of the NIE project in all the different engagements with the researchers, but he also happens to be the one that is administering this one. And what we have is they run on this large-ish cluster, large for us cluster, all these computations, and they actually, what they're wanting to do is their big runs are all on the national labs, all listed above, and they generate a lot of data out there that they want to be able to pull back, but it's just too much. And I can't actually characterize what too much is, but it's enough that they don't feel it's worth their hassle at the one or, well, it's certainly the 1 gig kind of bandwidth to be pulling it back. What they would like to do is pull it all back locally to this Huawei, interesting story there, but a Huawei, about a petabyte of storage we have as a part of this new cluster. This cluster came up over the past year, and be able to do a bunch of post-processing and generating videos and things like that they're unable to do now. So what we're working on, the Xiaofeng, the guy who's working with them as their administrator and working with us, the next challenge is to figure out how to take advantage of at least up to the 10 gig kind of capability of transferring all this data, getting this data from all the national labs down to the cluster so they can do all their post-processing work locally, which this is the second round of cluster environment that we've worked with them on, and they've been wanting to do this since the first one, so that's 6-7 years ago that they've been wanting to be able to get data out of these facilities down locally so they could do all their local kind of transformations. One of the recent features we added was a link, a dedicated link from the data center that's fiber. So right now it's at 10 gig to this nice 3D visualization system they have over in their research areas. They're wanting to be able to also steer, sort of real-time visualize the simulations they're running, and I think ultimately be able to steer the simulations that they're running, at least on our local cluster, and they even talk about it on the bigger clusters. The last one, I only have the name here. It's sort of describing the CBSE, Center for Biomolecular Science and Engineering. Their Cancer Genome Hub project is located at SDSC, San Diego Supercomputer Center. What it is an archive, well, sort of a storage site for all the genomes that are being sequenced as a part of NIH's Cancer Genome Atlas project. And that was a large sort of engineering effort we did with them to figure out where to locate that, where it could have both the data center capacity and the networking capacity to basically store genomes that are being sequenced at medical centers all over the country, and then feed them back out to researchers' genome analysis centers all around the country, where the latter, the data going out, was the big data. Their target is for the TCGA, it's TCGA, the Cancer Genome Atlas project, was 1,000 genomes, I think. It was certainly 1,000 or 2,000 genomes. Storage-wise, it was like 2 or 3 petabytes, as I remember, and all the in and out and the amount of bandwidth they were going to need. So that's located at San Diego Supercomputer Center. What they do locally is back it up. So all the development of the interface and all the system itself is done locally, and the big bandwidth they need is being able to transfer data from SDSC back up to Santa Cruz to put it to tapes or something. They have a fairly elaborate system of keeping copies of all these genomes. The idea being these are cancer genomes, are sort of very valuable things that people are able to learn lots of lessons from, and so they have requirements from NIH to have it archived in a way where nothing's lost. And right now, I should also have mentioned on this, in the SCIP cluster, what their loads are looking like is on the order of 10 terabytes of data a couple times a month. Right now it takes them days, 2-3 days to download this. They feel that there would get a lot of benefit if they could do it quicker. So and I'm not sure where they're going with that, whether they want to download it more often or what, but they're hoping to get it from days to overnight. These guys are, the main thing is just to improve their throughput to be able to be transferring all this stuff. They've been experimenting with different types of like grid FTP kind of stuff. UDT is another library for doing high-speed transport layer kind of communication. And so they're open to anything we can come up with. They're basically, we're talking to them about using some of the Dyn stuff or the layer 2 services to try and get their stuff transferring quicker. And so that's TBD exactly how we're going to pursue that, but that's the third major driver. Out of all this, we've begun to find out about folks in other parts of the campus, Ocean Sciences, some other users who have clusters and who have needs for being able to use the facilities of the Science DMZ that we're going to be looking to over the next couple of years of the project. Everything for me.
Okay, thanks. So that's sort of the overview of what we're up to. We were kind of hoping to have a bunch of questions to talk about why we're doing things in different ways. What sort of controller plane are you anticipating, Eric? That's an open question for us. One of the things that we at Santa Cruz have run across is that this is really a project that sits a little bit outside of the normal network operations sort of project, and we're implementing it with some folks, actually some of them funded through the CC-NIE grant, that are not our regular NOC operations staff. And so that's a little bit of a challenge that's ahead of us, is how to integrate the operation of the Science DMZ with the the regular day-to-day network operations. How do we set service level expectations for this? It's lower. It's not, doesn't have the same sort of path diversity that the production network does. And how do we communicate that to the folks who are the potential users of the resource, the folks who are interested in putting their project here? One project where we ran into this was with the Genome Browser. It's kind of the part of the genomics group, and there are pieces of their work that will benefit quite a bit by seeing the high data transfer rates, but the Genome Browser is a public-facing service. It's expected to be up all the time, and it takes hits from everywhere. So what we decided to do was to parse that browser chunk off, leave it behind on the production network, and do enough upgrades to the production network to give them good, reliable service. But that's not the thrust of the CC-NIE grant. How's that worked at your campus, Roger? Have you got projects that you have to set expectations for with the users?
Yes, but it's been... This is going to be short, but it's been really relatively easy to set the expectations for the users, because we went in there offering them something that wouldn't cost them anything and would be 10 times as fast as what they have now, and made it clear that the worst that could happen would be if it would go down every now and then, and they'd be back to the speed they have now. So it was just how we put it to them.
So do we have any other questions for the panelists? Okay, we've got one back here. Would you mind?
Yeah, I'm dual master from NASA, and one of the things that's kind of interesting I've seen from most everybody, not everybody, but there seems to be a trend to put projects, rather than have like a common data transfer node that everybody is sharing, it looks like you're sort of trending towards per project DTN. And I'm assuming that all the security and authentication of users and security and all that kind of stuff is done by the people who own that project, which maybe absolves the central group from worrying about that. But I mean, it does have certain security implications. So it's just an interesting trend that I'm seeing.
So let me see if I got the question right. It's about the placement and the ownership of DTNs in this world. Is there a central campus managed high-speed data transfer node that everybody can use, or do we see that DTN as another sort of little thing that's funded project by project, and that for which the security implications can be delegated to those projects?
Yeah, I guess I'm wondering if this is a conscious choice or just how it evolved, because it does seem to be a trend, I guess.
Yeah. Brad?
I can give a quick comment. We started based on the assumption that people were going to basically be doing their own, just from the conversations we had in the beginning, but as we were preparing the proposal. As we've started wading into these conversations about actually implementing it and thinking about how to actually the technology behind this, the research, the groups themselves have started, as well as some of the participants like the Xiaofeng, who I was talking about, who manages the Hyades cluster, have started suggesting that we should go to just one centralized kind of beefy DTN and eliminate the hassle of them trying to do this on each different project. So I think, if you agree, that that's pretty much where we've been. A surprise out of the past couple of months, the conversations over the past couple of months has been, they've been sort of volunteering, hey, could we just do some, well, actually, I should also say, we sent a couple of the folks to the workshop at Berkeley recently, where it was all about Personar. So part of it may have been they may have drunk a little bit of the Kool-Aid while they were there and started saying, hey, why can't we have one of those? But this is something that's been coming from the researchers back to us recently.
I think for us, there is a kind of some DTNs already implemented that are project specific or group specific. I think that might be because of the fact that the central campus wasn't providing something, and so they had to make their own thing. And once they make their own thing, it wasn't necessarily something they shared. I'm hoping that we can kind of rectify that. I don't have a problem with them running their own nodes if they want to, if they think it's easier or more efficient, or they just enjoy doing it. But I want the campus to have something we can provide, especially for researchers that wouldn't be able to create their own node. For researchers that have data transfer needs, but right now they're FedExing hard drives around, if we can have a data transfer node that's relatively turnkey for them to use, and we can say, here it is, go ahead and use it, and hopefully make their research better, faster, more efficient because of it. But I don't think that we necessarily want to encourage a high level of duplication of data transfer nodes.
The problem is pretty entertaining at Davis because several of the research clusters are in the data center, and the data storage nodes, transfer nodes, are virtually sitting next to each other. But what it comes down to is each data transfer node is associated with a project, because when they get the grant funding, they have to spend that money on that project. They can't take a third of what a data transfer node costs out of the grant funding and add it to what some other researcher can contribute. They're stuck.
So my question is for Roger. Don't sit down.
Oh.
But I guess maybe a more general question is, what if the 100 gig link goes down? Where does traffic go? Is there a fallback path on the DMZ network, or does it go to the campus network?
It fails over to going through.
Could you repeat the question, please?
Oh, what happens if our 100 gig link goes down? What happens is it fails over to a link that goes to the production network border through a firewall. So they're just back to, you know, what they had before.
Check, 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 check.
On the topology that we're going to be putting in place, if the 100 gig goes down, there will be a 10 gig link into the campus border, and that's where it will fail. It gives us an opportunity to congest things, and there's no solution to that until we get more fiber in.
For us, the Science DMZ connects through the border already. So if the 100 gig link from our border to the CENIC networks fails, we would start using our other link to the CENIC networks through our other border router. That, again, possibility of congestion, obviously much less bandwidth. We already have the fiber. We would need to upgrade it with DWDM and get some optics, 100 gig interfaces. But obviously, it would be preferable to have two of them. We're very grateful that CENIC is providing us one, and we'll use it. And once we have the ability, we'll get a second one, so that congestion won't be as much of a concern in a failure situation.
Any other questions? Yeah.
What's the nature of the traffic? These are like repositories. Are the downloads big and then people pull pieces of data out? Or do they go in chunks if the whole file transfer succeed or not succeed?
So the question is about the nature of the data, if they're large file transfers and then small chunks of it are used, or if the entire file is used. I can't necessarily speak directly to it. I can speak about what I've heard and what we're planning for. One of the possibilities is that it is large files and the entire file is used. In that case, the data would be pulled into the fast data transfer node through the Science DMZ. And that's the part that has much more performance considerations, especially once you get even a tiny bit of loss on a long distance transfer. Your performance just goes downhill tremendously quickly. But once the data is on campus in the Science DMZ, you can have slightly less perfect performance and still do a fast transfer across campus. So that's one possibility, is that they pull it from the other side of the world onto campus and then pull it across campus to their local machine cluster, whatever they're doing. I imagine it's also possible that they would want to get the data locally and then just take parts of it, but they need to get all of the data in a single transfer and then figure out what they need later rather than figure out what they need as they're trying to go through the data. Somebody else have more of an answer?
Not much more. That was pretty complete. All the projects that I showed on that board are using large files, 1 terabit to 10 bytes rather, and they are downloading the whole file to the data transfer node. They usually have 2 interfaces on the data transfer node. One of them has its stack configured for long haul transfers, which is quite a different configuration from the short haul.
The skip use that I was talking about earlier, the LHC downloads, is on the order of 10 terabytes, and they do it in little pieces of, I think, like gigabytes each. The Hyades, as far as I know, is going to be large files. I don't have a good sense of what the general size of those are. And the genomics guys are transferring genomes. That actually, it's interesting, the protocol they use to in and out of SDSC is a BitTorrent-based protocol, so it's all chunks. The chunks are pretty small. I'm pretty sure what they're doing as far as the backups, though, are moving full genomes at a time, and those are 1/4 to 1/2 terabyte each, is what the pattern looks like.
So it seems like one of the things that the science project people do is try to come up with protocols that compensate for loss and poor performance in the network. On the network side, we don't always understand what they're thinking about with some of the protocols, and they don't always understand how to give us data on the failures that they see. So, when in working through this problem with the skip cluster last week, we finally got, a whole bunch of people in the room at the same time and made some progress. But that's a real expensive meeting. And I think as we learn how to ask the science people for data about their problem as if we're doing an experiment, they can help us with that. And then there's another sort of fork of this question, which is even being ignorant of what the protocols are, we see the flows. And one of the things that we're hoping for SDN is that if we can recognize where the big flows are going, that we can pick those out and switch them on the more optimized path. In order to do that, we don't have to necessarily understand the protocols that are being carried on those flows. Others? Yeah.
So at Davis' diagram looks like maybe you mentioned a little bit, but interested in what sort of visibility you have for campus IDS or security groups into these new big huge links and how you're doing that, and also whether you're trying to segregate only certain traffic on the big links or allow everything from those projects.
Basically, our security group has no visibility into it. They're very nervous about that. But we reassure them that it won't get away from this Science DMZ. The visibility that is there is a mirrored port that hacking professor has, and we mirror it to different links to give him visibility into the links he wants to see. Is that everything? Okay.
So I also have a question for you, Roger.
Yes.
So my question goes to the sharing of the DTN portion and sort of the researcher or OpenFlow SDN portion, and have there been challenges with sharing some of that infrastructure?
Not really. The researchers that are using the SDN testbed and the laboratory resources are all in the same group. And they sit down at a table and they figure out when, who's going to use it and what resources they need on it, hook it up and go.
Does this traffic go as TCP traffic, so you send it back and get acknowledgement, send it back and get acknowledgement, or how, do you have a different protocol you're driving it across for these high-speed links?
Most of the time, they're using a souped-up version of FTP called Grid FTP that runs more than one stream at a time. And the idea there is that if a packet gets dropped because of checksum error, then it only slows down that one stream and the rest keep on plugging. Makes a big difference in how big the sawtooths are.
No further questions? All right, well, let's thank this collective panel.